Imagine your application just went viral. Suddenly, you don't have 100 users, you have 1 million. In the beginning, a single server was enough to handle the traffic, but as the requests pour in, that server starts to struggle. The CPU spikes to 99%, the memory is exhausted, and eventually, it crashes. This is the single point of failure nightmare. To survive this, we can't just buy a bigger server indefinitely. That's vertical scaling, and it has a ceiling. Instead, we need to scale horizontally by adding more servers. But how do we decide which user goes to which server? This is where the load balancer enters the stage. It sits between the users and your server farm, acting as the ultimate traffic cop for the internet.
At its core, a load balancer is a device or software that distributes network or application traffic across a cluster of servers. Think of it as a receptionist in a busy office. When a client arrives with a request, the receptionist looks at the available staff and directs the client to the person best suited to help at that moment. This ensures that no single server is overwhelmed while others sit idle. This process provides 3 major benefits. First, scalability. You can add more servers as traffic grows. Second, efficiency. It optimizes the use of your existing hardware. And third, reliability. If one server goes down, the load balancer simply stops sending traffic to it and redirects users to the healthy ones. This creates a seamless experience for the user, who never even knows that a server failure occurred behind the scenes.
How does the load balancer choose where to send the traffic? It uses specific algorithms. The simplest is round robin. It works exactly like a deck of cards. The first request goes to server A, the second to server B, the third to server C, and then it loops back. But what if server A is much more powerful than server C? Then we use weighted round robin, giving the beefier server a higher percentage of the load. Another popular method is least connections. Here, the load balancer tracks how many active requests each server is handling and sends the new user to the one that is currently the least busy. For applications where user state matters, we have IP hashing. This uses the client's IP address to consistently map them to the same server, ensuring their session data remains available without complex backend syncing.
Load balancers generally operate at 2 different layers of the OSI model. Layer 4 load balancers work at the transport level. They only look at TCP or UDP information, basically the source and destination IP and ports. They are incredibly fast because they don't peek inside the actual data packets. Layer 7 load balancers, on the other hand, operate at the application level. They are content aware. They can look at HTTP headers, cookies, or even the URL path. This allows for much smarter routing. For example, you could send all requests for images to a dedicated image server cluster, while sending API calls to a different group of servers. Layer 7 is more resource intensive for the load balancer, but it offers the granular control needed for complex microservices architectures. A load balancer is only useful if it knows which servers are actually working. This is managed through health checks. Periodically, the load balancer sends a ping or a specific HTTP request to every server in its pool. If a server responds with a 200 OK, it's marked as healthy. If a server fails to respond or returns an error code, the load balancer immediately stops sending it traffic. This process is automatic. Once the server is fixed and passes the health check again, the load balancer gracefully reintroduces it into the rotation. This self-healing capability is what allows large-scale systems to maintain high availability even when individual components fail frequently. Their session data, like a shopping cart, might be stored in the memory of server A. If the next request from that same user is sent to server B by the load balancer, server B won't know who they are, and the shopping cart will appear empty. To solve this, we use sticky sessions, also known as session affinity. The load balancer identifies the user via a cookie and ensures all their requests during that session go to the same server. While this solves the immediate problem, it can lead to uneven load if one sticky user is much more active than others. Modern architectures often prefer a centralized session store, like Redis, so any server can handle any user's request without needing stickiness.
In a cloud environment, load balancers work hand in hand with autoscaling groups. As the load balancer detects that the average latency is increasing, or the existing servers are reaching high CPU utilization, it triggers an event to spin up new server instances. The load balancer automatically registers these new instances and starts sending them traffic within seconds. Conversely, when traffic drops, say at 3 a.m., the autoscaler can terminate unnecessary instances to save costs. The load balancer gracefully drains the connections from those servers before they are shut down. This elastic nature is the secret behind how companies like Netflix or Amazon handle massive surges without manual intervention. If the load balancer is the gateway to your entire system, what happens if the load balancer itself fails? To prevent this, we use high availability pairs. We deploy 2 load balancers, one is active and the other is passive or standby. They use a protocol like VRRP to share a virtual IP address. Both load balancers are constantly talking to each other through a heartbeat signal. If the active one stops sending heartbeats, the passive one immediately takes over the virtual IP and starts processing traffic. The users don't see any downtime. In very high traffic scenarios, you might even have multiple active load balancers using DNS-based load balancing to split the initial entry point traffic among them.
For a truly global application, a single data center isn't enough because of the speed of light. A user in Tokyo shouldn't have to wait for a request to travel to a server in New York. This is where Global Server Load Balancing, or GSLB, comes in. GSLB uses DNS to direct users to the data center geographically closest to them. When a user types in your URL, the GSLB system looks at the user's IP, determines their location, and returns the IP address of the nearest regional load balancer. This reduces latency and provides an extra layer of disaster recovery. If an entire region goes offline due to a power failure, the GSLB can instantly reroute all global traffic to the remaining functional data centers.
To recap, handling 1 million users isn't about one giant server. It's about an intelligent distribution of labor. Load balancers provide the scalability to grow, the health checks to ensure reliability, and the algorithms to optimize performance. Whether you're using a simple round robin at layer 4 or complex path-based routing at layer 7, the load balancer is the backbone of modern web infrastructure. As you design your next system, remember, build for failure, scale horizontally, and let the load balancer handle the heavy lifting of traffic management. Thanks for watching this deep dive into load balancing. If you found this helpful, subscribe for more system design explainers. See you in the next one.